Good day, students. Welcome to the first recording under Module 5, Chemical Changes in Fats and Oils. Before I actually get into the content related to this chapter, the most important message that I have for you is that you need to obviously consult the textbooks in terms of the references. And this part, as you can already see, I'm only starting to record from slide number 20. So the previous 19 slides talk about the structure of the fatty acids or the triglycerides, how it actually affects the functionality, nomenclature as to how do you name fatty acids using both the systematic and common laws. So what I require from you as students is to go and recap on this, because this is work that we've done in Food Chemistry 2, and it serves as a foundation for you to be able to understand all the chemical reactions. So that is work that you have to do on your own. Go and recap on the properties of triglycerides, and then from there you'll be able to understand these two chemical reactions. So as I already mentioned, we're going to talk about the two chemical reactions, which are the deteriorative chemical reactions. There are also other chemical reactions that are desirable, like your hydrogenation and interesterification. The reason, obviously, we're focusing on hydrolysis and lipid oxidation is that it becomes a problem in the food industry because it affects the acceptability of food products once this chemical reaction have taken place. So for us studying them, we need to understand how they go about taking place and how can we go about preventing them. Okay, so down to the actual content, hydrolysis versus lipid oxidation. Many times people actually confuse the two. So I thought the first thing that we need to do before talking about the actual chemical reaction is to differentiate between these two chemical reactions. So in terms of the similarities, it's quite obvious that they all affect fats. So this two chemical reaction takes place on an actual triglyceride, but the difference will be where on the actual triglycerides do this reaction take place. So in terms of hydrolysis, hydrolysis takes place on the ester bond, where the glycerol and free fatty acids form the ester bond. That's where they take place. Meanwhile, lipid oxidation, on the other hand, takes place on the actual hydrocarbon chain of the fatty acid. So those are the two different sides where this two chemical reaction takes place. And what are the differences then? The differences would be, in terms of hydrolysis, for it to take place, you need enzymes, and some of the enzymes that's required are your lipases. And then it also takes place in the presence of acid and alkali, especially at high temperature. And once this hydrolysis has taken place, the breakdown products obviously contribute to the odors or the sensory perception of the food. And the sensory perception that you get when you are consuming a food product that has undergone hydrolysis is known as hydrolytic rancidity. Coming to lipid oxidation, it's quite different. Lipid oxidation, like we already mentioned, it takes place on the actual hydrocarbon chain, and it takes place in the presence of oxygen. That's why it's called lipid auto-oxidation. It's catalyzed by enzymes. Also, we have enzymes lipoxygenase that also acts as a catalyst. And then there's metals like your iron and your copper that also accelerate it. And then, just like any other chemical reaction, it's further its reaction rate is further affected by an increase in temperature. And what happens is that when the lipid has been oxidized, the products that are formed, they contribute obviously to the sensory attributes of that food product, and that is known as oxidative rancidity. So differentiate between hydrolytic rancidity and oxidative rancidity. When it comes to hydrolytic rancidity, it affects the smell and the taste. However, with oxidative rancidity, it affects at least 3 of the attributes, which happens to be smell, taste, and color. So you need to be able to differentiate between the two. So moving on along, Now we have to focus on hydrolysis mechanism. As I've already mentioned that hydrolysis takes place on the ester bond of the triglyceride molecule. Just to go back a little bit of recapping, we all know that when glycerol and free fatty acids form due to the process of esterification, water is actually lost as a byproduct, and that is known as condensation. So hydrolysis is actually the reverse or the opposite of condensation, whereby water is required as a catalyst with other catalysts like your lipases, which are enzyme, acid and bases, to actually break down the ester bond that was formed during condensation. So repeating, it's actually a reverse reaction of condensation. So once the lipid has been hydrolyzed, the fatty acid is actually separated from the glycerol, and then you form what we call free fatty acids. So as I already mentioned, that enzymes, especially lipases or phospholipases, are actually responsible for the cleaving or breaking down of the ester bond. So where will these enzymes be coming from? There's two types of enzymes. The one enzymes will be some inherent enzymes like that are found in the lipoproteins, like your lipases that are inherent in the raw material. And secondly, the type of enzymes that will also be cleaving the triglyceride molecule will be enzymes like your lipases that are coming from microorganisms that actually contaminate the actual food product. So we already mentioned those will be inherent lipases, and then there will be lipases that are being produced by microorganisms that would have contacted or contaminated the food. And then if it's not the enzyme that's causing the cleaving of the ester bond, it can be acids and bases. And as we already know, when we did saponification, we used a base, sodium hydroxide, to form salts of fatty acids. So at high temperatures, you can actually cleave the ester bond using acid and bases. So depending on the extent of the chemical reaction, what happens is that you can have what we call partial or complete hydrolysis. So partial hydrolysis is when you have this triglyceride, and then due to the extent of the hydrolysis, you might just end up with one free fatty acid and then left with a mono or diglyceride. That's partial hydrolysis. So, but then you can also have complete hydrolysis, whereby the whole triglyceride is cleaved, whereby you will find glycerol as a byproduct and 3 fatty acids that are free. So that is called complete versus partial hydrolysis. So we had already mentioned that after hydrolysis had taken place, because of the increase in free fatty acids in the food, it therefore brings about the taste and smell, and that is known as hydrolytic rancidity. But then later on we'll still talk about, in terms of this hydrolytic rancidity, which types of fatty acids are actually more affected when it comes to hydrolytic rancidity. Okay, so like we already mentioned, that those glycerides are actually cleaved into free fatty acids and glycerol, and this is a phenomenon that we usually do when we're forming soap in a process known as saponification. Okay, so like we already mentioned, that in terms of hydrolysis, you get the enzymes that are actually breaking down. If enzymes are the one responsible, there's two types of enzymes. The one that is inherent, and these enzymes are widespread in a whole lot of lipid containing tissues, or it can be an enzyme that's coming from microorganisms that contaminated the food, or maybe microorganisms that are indigenous to that food product. Okay, so what happens, what makes these lipases perfect for the reaction they catalyze, is that these lipases, they usually act in systems such as your emulsions, your heterogeneous systems, and especially your emulsion oil and water, whereby they are found in the interface, and that's when they're able to cleave those ester bonds. Okay, so what happens is that the most significant consequence of lipase activity in foods is definitely the development of a harsh acrid taste. That's where we talk about the hydrolytic rancidity. It's known as harsh acrid taste, and that's due to the liberation of the free fatty acids. So by increasing the free fatty acid levels, then you bring about this harsh acrid taste. However, when it comes to your hydrolytic rancidity, which is obviously the sensory that's perceived due to hydrolysis, what happens is that only your short chain fatty acids are the ones that can actually contribute to that odor or off flavor. So let's say you have a triglyceride that is made up of 3 fatty acids, which is your short chain fatty acids, medium and long chain fatty acid, and then in those we have complete hydrolysis. The taste and the odor will only be coming from the short chain fatty acids. So the medium chain and the long chain cannot be perceived, even if they have been hydrolyzed. They cannot be perceived. Their threshold is quite high, not as low as your short chain fatty acids. So they contribute to the flavor. But that does not mean that it's fine for hydrolysis to take place with long and medium chain fatty acids. It's still a disadvantage, and we'll talk about that later. Okay, so this hydrolytic rancidity, it's quite common in food products like your olives, in dairy, your milk, cream, and butter, in oil seeds like your peanut and soybean, and then in cereals. And the reason for that is that all these products contain inherent lipases within the system. And usually with things like your peanuts, your soybean, and your cereals, your wheat and your oats, the only time when this hydrolysis takes place is when maybe there's milling taking place, or milling and maybe separation of the wheat bran. And then there's also when the soya beans are actually crushed to express the oil. What happens is that usually in those systems, the lipases will be separated from the actual fat. But the process of grinding and the process of oil extraction pressing then makes those lipases available or come in contact with the actual lipids, and then the hydrolysis takes place. So in an actual cereal or oil seed, what happens is that when it's intact while it's growing there, hydrolysis does not take place, but it takes place during processing. Okay, so as I already mentioned earlier on, lipases activity occurs on the interface. On the interface, we already know the interface is that phase between the oil and the water, especially in your heterogeneous systems. And then lipase activity occurs there, and it's more rapid in finely dispersed emulsions, because obviously there's an increase in surface area, especially of your homogenized milk and cream, because by then it's like spreading it around. And we already mentioned that a high free fatty acid level in edible oils is objectionable, and this must be removed in the process of refining. Remember the 4 refining processes that you did in food technology 2: degumming, neutralization, deodorization, and bleaching. So in neutralization, that's whereby the free fatty acids are removed. And the reason for that, besides the fact that obviously they'll bring about the off flavors, very important is that free fatty acids are removed, because then they will affect the lipid oxidation rate later. So they are prone to oxidizing faster than your normal fatty acids that are actually esterified to a glycerol. And we'll talk more about that when we talk about lipid oxidation. So as we already mentioned, the negative impact of hydrolysis, the high acid value. Remember, when you are neutralizing your fat or your oil during refining, you have to neutralize the acid with sodium hydroxide. So the more the free fatty acids, the more sodium hydroxide is required, which is then means money and energy. So it then results in high processing costs for the person that has to, or for the company that has to refine the oil. And then we already mentioned the sensory quality, consumer acceptance in terms of the free fatty acids level that will, especially if you have your short chain fatty acids, whereby you can taste the harsh acrid taste that comes from due to the end products. And then as I already mentioned, chemical reactivity, your free fatty acids are more prone to oxidation than your fatty acids that are actually esterified. So as much as maybe your long chain fatty acids might not have off taste in terms of hydrolytic rancidity, but then they accelerate lipid oxidation, therefore accelerating oxidative rancidity. But as much as we spoke about the negative impact of hydrolysis, hydrolysis is not bad all the time. In actual sense, hydrolysis is actually one of those chemical reactions that are desirable also in the food industry, especially in your dairy products like your cheeses and your fancy cheeses, your camembert cheeses, Roquefort, and all those other mold cheeses, whereby the ripening of those cheeses actually has to do with the hydrolysis of the fat, so it brings about the texture. So when you talk about mature cheddar versus normal cheddar, so mature cheddar would have had more of free fatty acids being hydrolyzed. So hydrolysis is not as bad at all the time, but it depends in which product is it taking place in. So if it's taking place in your cream and your butter, we don't want it because obviously it affects the taste, but it is required at some certain level in products like your cheeses, and as I already mentioned, those other fancy cheeses, Roquefort and Camembert. Okay, so the next section will deal with lipid oxidation.